So I've known Daulet for many years, now around maybe 8 or 9 years. And he's originally from Kazakhstan, but he did his studies initially in Turkey. And then we met in Europe, in Sweden, at KTH, where he was doing a postdoc in the group of multidimensional. So during his PhD, initially he was working on droplets and surfactants and viscoelastic flows. And these viscoelastic flows is how I started also working with Daulet when we were both postdoc at KTH. We were in the same room, actually, and in the opposite desk. So we used to see each other every day. And after Sweden, he liked the northern country, so he decided to move to Finland. So initially in the university, and then since 5 years ago, maybe. He
22.
Okay, so 4 years ago, yeah, he moved to the Meteorological, Finnish Meteorological Institute. And so today's talk of Daulet is called How Air Moves and Affects Us, Simulations of Urban, Indoor, and Human Air Quality. Thank you.
Thank you. Can you hear me? Yeah. So thank you for the introduction, Marco. It was nice coming here. I guess I should also thank TSVP for inviting and let me stay here for several months. Yeah, as Marco just introduced, my main background is in mechanical engineering, so on droplets and viscoelastic surfactants. So it's not directly related to, I'm in the Meteorological Institute, so it's not directly related. So whenever I met someone, so they ask where you're from, I say, I work in the Meteorological Institute, and say, okay, the next question, what are you working on? And I say, yeah, I'm working now on the multi-phase flow, basic lung flow, surfactants. So it doesn't really look like it's related to the Meteorological Institute. And so I received this question, like how it's related, how do you work in the Meteorological Institute? Because it doesn't look like the topic directly relevant to the Meteorological Institute. And then, yeah, and the second question, when I just joined the Meteorological Institute, my colleagues from the other institute, they were asking, so why is the weather is like this today? In your app, it says that the weather should be rain and today is sunny, or is the vice versa. Yeah, so to answer those questions, I decided maybe this should be then the topic, how actually the topics, what we do in the Meteorological Institute is related to the topic I'm working on now. Yeah, so I work in the Finnish Meteorological Institute. So as in other Meteorological Institute, we do work on the weather forecast, but that's not our main job. We have some department which always work on the weather forecast as in other institute. But me personally, I work in the atmospheric dispersion modeling. So we work mainly on dispersion modeling. Our head of the group is Ari Karppinen. So in the atmospheric dispersion modeling, we work on the different scales. So we work indoor or even smaller, like flow in the lungs, because it's a related dispersion, but we also work on a much larger scale. So we go up to global scales. So what do we do? I'm particular in the fluid dynamics because I'm coming from the mechanical engineering department. So of course, we do atmospheric dispersion modeling, and one of our main topic, and this topic of our current my talk is about the air quality. So we do some local scale air quality. Then we do also global mesoscale air quality modeling. Then we do, because we do air quality modeling, we do also the forecast. We do maritime emissions. We do urban boundary layer flow. We do atmospheric bioaerosol modeling. We do modeling the fires. And then if a chemical accident happens somewhere in the city, then we also try to model what are the consequences of those chemical accidents on the city. And then we do also fires, dispersions of the fires. So I decided to talk about the air quality forecast, to have more research, but I wanted to do like only for research for some specific teams. So one of the teams is called CLAM. Its main contributors are Mikhail Sofiev and Rostislav Kuznetsov. It's an air quality forecast, and this one, the CLAM team is a more global one. So within using the CLAM, you can have a 4-day forecast for the air quality over the globe, Europe, Northern Europe, and Southeast Asia. So we can also have a 5-day forecast of pollen distribution over the Europe, Northern Europe. Then we can have also a 5-day forecast distribution of the smoke over the globe. So this CLAM is a bit bigger model for the global scales. And we have also a smaller scale for the urban flow. So this is done by Lasse Johansson. So this one is a bit smaller, but that's why we can have a real time as well as the forecast air quality. So currently it's only operational in Finland. It's in Helsinki and Turku. But it has been shown that it's also actually portable, and you can use. It has been used in China, in Nanjing, in Langfang, and it was in India, in Delhi. But of course, myself, I'm not in their team. I'm working mainly on the computational fluid dynamics team. So our team is quite small, so we're only 7 people in our team. Our head is Antti Helsten. So we're mainly working on the modeling of airflow. So until recently, most of the studies were only in the urban flow. So urban flow, all the mountainous environment. And then we have different projects, and in these different projects, there were various locations in Europe. So here I just show some samples. So this is the Helsinki, so city center of the Helsinki. And then we have the airfield, we studied the airflow over the Helsinki city. And then this is another one. This is actually so more mountainous region. It's Guadalajara in Spain. So you can see the flow field over the mountain region. But then we have different projects, and what we do, we compute the wind field, and then we use for the air quality analysis, for the road safety, wind hazard, etc. But then COVID happened, and then everyone were indoor, and then we had different more projects, and then several projects we start shortly. We start moving to the indoor simulations. So we start doing more indoor, and now we not only doing the urban flow, but we're also starting doing more indoor flow. So it's still related because it's still airflow, it's still this dispersion modeling. And then more recently, I received my own grant, and then I start working on the airflow in the lungs. So today I will mainly explain about research which we do in our group. So as I mentioned, we do mainly urban air environment. So this is the flow field, instantaneous flow field over Helsinki city center. Then we move to the indoor air movement, and the indoor. So here, for example, is the air inside the restaurant, which is also in the Helsinki city. And then this is more recent study is where the airflow so it's in the upper airways, but we also actually study what's happening more below, but it's more respiratory airflow. So as I said, mainly we're doing urban flow studies. So in this particular case, we were taking down the Helsinki city. So we take the Helsinki city, and then so whenever we do the urban flow studies, we have to take into account the actual geometry. So we have to take into account real topography of the city. So that's always how we do. So in this case, we take real urban environment of the Helsinki 3D open access dataset. So this is the real data. Then we're using, for the urban flow case, we're always using this open source model. It's called Palm. So we're active users as well as we do actively developments in the Palm. So for this work in Helsinki, the main contributors is Antti Hels and Nick Alvin. So as a motivation for usual urban flow, we do, because we are a dispersion modeling group, we do dispersion and transport of different pollutants, to be dust, pollen, and something else. So we had actually one more project related to urban flow in Helsinki. So we were simulating one particular region in the Helsinki to support modern urban planning. So as you can see, we performed LES simulations, and then as I mentioned before, we use real urban environments. So you can see that we have actual buildings here, we have the actual vegetation, and the dataset is actually based on the real data, which you obtain from the open dataset. So another study is, this is from Turku, so not to be confused with Turkey. It happened to many people. Someone was speaking about, I'm from Turkey. So you're from Turkey? No, I'm from Turkey. It's in Finland. Okay, so in this study, it's an EU project response. And so here my colleagues, Jukka-Pekka Keskinen and Lasse Johansson, were working. So here what our group, our team was trying to do is can we actually improve our air quality model in Fuser, which is on the local scale, so urban scale model, by taking into account more accurate wind field from the palm. And so here we take into account the real urban environment, and which is based on the data taken from the Turku's LIDAR data. And you can see that, so this is how this doesn't work. You don't, okay, you can see here. So so on the left, it's some part of the Turku, and we can see the concentration of the PM 2.5. And so the more yellow one is the high concentration, and the more dark one is a low concentration. Another study was about ship emission. So actually the dot is the ship is departing from the Turku harbor. It's going toward the Baltic Sea waters. And you see how the plume behind the ship is changing with time. You can see that the ship is actually moving now. Now it's departing. So in this study, so this was just an example, but what we try to do, but in the previous slide, we tried to do to improve our air quality model working on the urban environment, but here we're using more global scale model. It's a CLAM, as I mentioned before. We have a bigger model. It's called CLAM. So can we use this bigger scale model with the more defined velocity field obtained from our simulations? So here was the concentration of sulfur dioxide, but of course it can be done for other dust and pollen, and we have some now ongoing study where we also studied the pollen transport. Yeah, so we started from outdoor, but we thought, can we go for smaller scale? Can we go to inside the buildings, inside this outdoor simulations? And then, yeah, so we had one project with the dentists in Helsinki. So this is like a dentist room, a typical dentist room we have in Helsinki. And yeah, so there's one doctor and maybe one nurse, and someone is laying down who wants to treat his teeth. Yeah, so this was one of the case. Another case was one of the restaurants. So it's actually real restaurant in Helsinki. So we did simulation and we do also experiment measurements in the restaurant. And another one is the hospital waiting lobby. So this waiting lobby, like a corridor-like lobbies, it's very typical to have in the hospitals. But what we saw that maybe due to different regulation pre-COVID or due to maybe some old buildings, that ventilation was not so good in this waiting lobbies, and especially because if it's in a hospital, so it means that most of the people waiting in the lobbies are actually sick. So it was important to study what would be the effect of the air purifier if you put in the lobby. We have some other projects also, which is not shown here. One of the projects is Active Mine. So we have collaboration with them. We studied the air quality modeling inside the active mines. Yeah, so for the indoor flow, yeah, as I'm standing here, so if I would be sick, then I would generate some droplets. And the big ones, as you can see, then the big ones will just fall down very close. But then it was shown also but the small one, that's the tricky ones are the small ones. So the small one I produce, they stay in the air for a longer time. And those are the actual which go from me, and then they make you sick because you inhale them, because they're very small ones, you don't see them and you just inhale them. Yeah, so this was a study from the real restaurant case in Helsinki. So people are sitting there, and then one customer who is sick, who is speaking too loud because he's explaining something, you can see that it's the concentration of the aerosol he's producing. So the black one is it means it's a high concentration. It's because it's very close. So he's producing a lot. As it goes further, the concentration is getting lower and lower. And so we also put the real air purifiers, and we saw, like, does it really help? Yes, and indeed, you can see that purifier helps because not much concentration shown going beyond the first purifier, because the purifier actually takes it cleans the concentration in the room. So for the indoor flow studies, we try to study dispersion and transport of the aerosol. And then again, we use the same solver. We do development on the solver to use indoors. And then we use real environment. So we take also realistic ventilation condition. And we studied different strategies to reduce the risk. And so what we came up here in the study is that air purifier indeed helps, but with its own limitations, of course. Yeah. Yeah, but so in this study, we also took measurements. So we did both measurements at different places in the restaurant, and we also, of course, we perform already the simulations. Then we compare our simulation data, time evolution of the concentration obtained in simulation and in experiments. And we use different metrics. And in overall, we show that we're actually quite in good agreement with the experiments. Yeah, another study, as I said, it was the dental room. So in dental room, so we assume it's a room. We have a 3-person, and maybe only one of them is sick. Let's assume, and then we have a table, and actually on table we decide. Let's see if we also put a fan. Do we have any effect of this fan or not? So we have an inlet, like in all the room, you have inlet where the pure air is coming, and you have outlets. And in some room, you have several of them. In some room, you have maybe one. So it's sucking out the air. So if there's inlet, there's outlet where the dirty air is coming out. And then there are different flow rates, of course. So what we wanted to study here is that can we come up with the improved analytical model to study the indoor air hygiene assessment. So like if in a typical room, if you have some treatment, and then depending on different conditions, you have a treatment for 1 hour, and if this is the mean concentration, this is 1 hour, and this is time. So you see as time progresses, of course, you stay longer, and then after 1 hour, say, okay, the treatment is gone, so please, everyone leave the room. Everyone leaves the room. And then depending again on the condition, you can see that even after 1 hour, for some condition, the concentration did not go to 0. So it means that for some condition, you have to wait even longer before you can take a new patient, because the concentration is still lingering in the room. Yeah, so we use the realistic dental room environment, and then we use realistic ventilation conditions. So the actual room was single unit, but we studied different effects. So for example, here I showed what happened if the room was actually quite bigger size, what would happen. And so here is the average concentration evolution in time. So here we have 2 cases. Here we have just the clean air is coming in and it goes out. And here's the mean concentration in time, how it evolves in time. And the second one on the right is if you put just a fan, so that if you enhance the mixing inside the room, does it help anyhow? And then actually you see as the time evolves, as time is increases, you can see that concentration increases here on the left when you don't have any extra mixing. So you have some regions with higher concentration, where on the right, because you have enhanced mixes, so it's more homogeneously distributed in the room. And because you have an extra inlet and you have sucking out from the outlet the air, that really helps. That makes the air hygiene in the room much cleaner. So so you see after the whole treatment, now we can see the room is more or less more homogeneous, more cleaner, whereas in the room where we do not have any extra mixing, enhanced mixing, then we can see some regions which has more concentrations. So we have with the high gradients regions, and then we saw that, okay, even with the simple fan or by somehow enhancing the mixing, we can reduce the overall concentration level inside the room. Of course, more studies, more post-processing or more research is performed to really improve how can we come up with a more simplistic 1D model which take into account various conditions like a bigger room, higher flow rates from the inlet, outlets, and etc. Yeah, so because with that improved 1D model, it can help doctors to say, okay, how long do we need to wait in this particular room so that the room will be ready for the next customer. Yeah, so Another one, as I said, so in this work, we work Mikko Auvinen and Antti Halsen. It's in our E3 Business Finland project. So in this room, it's one of the waiting lobbies in some hospital. And then we have people sitting there. And then in some cases, we observe that sometimes the ventilation is not working properly. And in some places, because it's maybe some very old building, they just rely on that people opening and always closing the doors when they're while entering or exiting the building, that would help the ventilation. But by showing the simulations and we also did the measurements, we showed that it's not really enough. You really need to do something else. You need to add the purifier. So this is one of the works which we have done. Yeah. So in the last part of my talk, it's about the respiratory airflow. So now we're still speaking about the air quality. So now where the sources of again, as mentioned before, we're a source which we produce this bad hygiene air, right? So in Muravska et al., they say that there are different ways how a person can produce actually those droplets. So one of the ways is you can produce them via mouth. So when you speak, when you sing, whatever you do, so you can produce them either between the lips or between your teeth. The second one in the larynx. So when you speak, when you say something, you can produce also some small droplets. Further down, you have a mucus layer on your lung, and then airflow mucus interaction due to the strong airflow mucus interaction. Then you can also create those small droplets. And the last one is the smallest one. Once you go deep in the lungs, actually they show that in some cases you can block the airflow. So this is the mucus, you block the airflow, and during the inhalation or exhalation, then you can break rupture this blockage, and then you create the small droplets. So yeah, so this is like our recent study. So we studied here particle transport from the vocal cords. So now you show the airflow in the vocal tract here. So this you can see so this geometry is real geometry based on some person, which they took a scan, and then we reproduced the geometry was reproduced, and then we performed the simulations. So we used 1 to 100 micron particles. We put them in the flow, and then we saw that at high flow rates, only the small particles from 1 to 5 microns. So you can see the green one, actually the big particles, they immediately stuck to the wall, but the smaller particles, and in this case, it's mainly 1 to 5, so only the blue ones and the smallest particles are mainly leaving the mouth. So other ones are filtrated. Then when we decrease the flow rate, slightly bigger, from 1 to 10 micron particles, we saw them exiting the mouth. So you can see now the still green ones are stuck, now slightly bigger, but it's still from 1 to 10 micron particles are leaving the mouth. Yeah. So the small particles are likely to exit the mouth, but the larger particles are mainly, as you can see, the green one, the larger one, are stuck, and they kind of filtrated by the tract, and only the small particle, which also lingers in the air for longer time. Then, yeah. So for this type of study for the upper airways, because there are a lot of studies, and it's quite typical that you can take patient-specific geometry. So you take for a particular person, you take the geometry, you take a scan, and then you recreate the actual geometry, and then you can do airflow studies and see if how the airflow is going through the actual geometry. But if you go beyond, if you go even to the lower generation, lower branches, like as Moros mentioned, that in some cases, what you see, you have, so the blue one is the mucus layer, and sometimes, in some cases, when the person is sick, you can see that the mucus is getting very thick. The material properties of the mucus change a lot. So then, when the mucus becomes very thick, the instability occurs, and then the liquid plaque appears in the lung. So when the liquid plaque appears there, then it's actually very difficult for a person to breathe. It's getting very difficult to breathe, and then you start to cough, and then you try to break this the plaque. But then that's the thing with the plaque, depends on the case. So if you're severely sick, this plaque becomes so thick that you cannot really breathe, and then it can even lead to lethal conditions. Yeah, but then even if you don't have such a severe case, then after the rupture, because after the rupture, so you break this plaque, it ruptures, it reopens, you start to breathe. But then what actually they observed, the experiments were done, and they saw that because of the rupture, during the rupture, the sound wave propagates, and then the sound can damage the epithelial cells near the rupture. So that sound is like the crackle sound is the typical one when someone is sick. So you go to the doctor, and doctor say, okay, let me hear if you have this crackle sound with the stethoscope, and that sound is coming usually from this rupture. And then that they were thinking about the study where they say, okay, actually every sound is you can say which sound to which sickness. You can correlate them actually. Yeah, so in the respiratory flow, so typically if we try to model this, how it happens, the airway is normally, it's flexible. So you have a mucus, then elastic instability happens, and then the airway closure happening, so that you have a plug. So now it's very difficult to breathe. So this is like a typical case, but then in some cases when someone is sick, so what it happens that the airway become very thick, so it become inflexible, so it's almost like a rigid. But we saw that even for those cases when the airway walls behave like a rigid, numerically we saw that the airway closure still can happen. So once you have this airway closure, then let's assume you don't have a very severe condition, then you inhale, and then finally you can breathe, and then you can rupture, you can have so what we call airway reopening, because now you start to breathe, okay, and then this crackle sound can happen. So it's actually very, very difficult to model. This problem is very difficult. So as we say, if you just take the small portion, so you have epithelial cells, you have a serous layer, you have a mucus layer, then you also have cilia. So you have a cilia which is moving. Then because of epithelial cells, you have fluid structure interaction. Because it's not rigid, it has to move. And there's a complex multiphase because you also have a surfactant. It's not a clean, and the surfactants plays a very, very important role here. Then the mucus layer is, unfortunately, it's not Newtonian. It's a highly non-Newtonian fluid, and it has very complex characteristics. So it's also very, very difficult to model it because it has highly non-Newtonian, non-linear characteristics. So yeah. Then with our collaborator and our collaborator, so they started, okay, so let's start step by step. So let's try to model simple airway closure. So we'll assume that, okay, let's do some simple experiments in a tube. And compare with our numerical methods. And indeed, there are more not shown here, but we can see that numerical model can really predict the closure. Yeah. So with the collaborators, it has been started to let's do step by step. So one of the easiest way to proceed was to say, okay, let's simplify everything. It's too complicated. We cannot tackle all the problem at the same time. We say, okay, it's a tube. It's axisymmetric geometry. It's a rigid wall, so no fluid structure interaction. It's very rigid. We don't have two layers because the layers are very, very thin. So numerically, it's very difficult to model that part. So let's say we have one homogenized layer, and then we have air. And then we compared with in the previous slide, we already compared. It was compared with experiment. It was in good agreement. And in the next one, say, okay, but can we go even more detailed analysis? Can we add serious layer? Okay, then two layers were added, and very different physics was observed. But then we said, okay, but the mucus is not Newtonian, and it's non-Newtonian. But what will happen if we change the layer instead of replace it with the viscoelastic model? So we try different viscoelastic models, and then we study the airway closure. Then, but then it's not enough to study just non-Newtonian effects. Not that there is also surfactant, and surfactants are very, very important part of the airways. So then surfactants were added to the model. And then more recently, we studied the airway reopening. So here we try to go a bit more deeper. So we say that, yeah, but mucus is not even viscoelastic. It's more complicated. It's elastoviscoplastic. So it has elastic, viscous, and the plastic effects. So it's more complicated. So we take into account elastoviscoplastic effects. And then we also added the surfactant on the interface. And actually, and this is again done in axisymmetric. So like up till now, many people tried to tackle this problem, but then up till now, it's simplified a lot because it's very difficult to tackle this problem. So it's usually not axisymmetric. So there is symmetry, and then it's usually either you put only elasticity or you put only surfactant, or so it is very, very difficult to take all these properties in one model. So even though you have them separately, but still we have not done, and in the literature, we don't know any study which took all the effects at once. So during my visit, I will try with Marco to make it in full 3D, to take into account all the non-Newtonian effect, the surfactants, and even the elasticity of the epithelial cells region. Yeah, so but why we study this? Because we want to say, okay, so after you have this liquid plaque rupture, so there's one theory that after liquid plaque rupture, you might end up with the droplets. So it is very important for people to know like how those droplets are generated, how many droplets are generated, where exactly in the airways those droplets generated, how they propagate. But up till now, most of the studies they were constrained only to axisymmetric. So even though the dynamics in overall look like axisymmetric, but the rupture itself and the generation of the droplet, it was shown in the recent study that you need to have the full 3D dynamics. And from the modeling point of view, it's very expensive. So I think it's only study what we know that they did in full 3D, and they studied rupture with the generation of the droplets for this case. But of course, it's still simplified model. It's solid walls. Then mucus is Newtonian. It is not Newtonian. It's highly complicated. There are surfactant effects, and they are not. So it is still very active research in this field. We still don't know many things. It's also very difficult to do experiments, even though they try to do some experiments. So we try to do both, like some groups do experiments. We do more on the simulation part. Yeah, so this is like a kind of state of the art, what is happening now in this respiratory airflow or liquid plug rupture, what we have. Yeah, so I think that was my last slide. Thank you for listening. If you have any questions.
Daulet, do you have any questions?
I think in the slides you showed us some simulations and experimental comparisons. What are those experiments like? Kind of setup?
I think it was the two liquids, but now I don't remember this experiment. But I think you can check it in the paper. So yeah, but it's a two liquid interface in a tube. But you have to check for the paper. Yeah.
Thank you very much for the nice talk. I'm interested in the urban flows.
Yeah.
Don't know if you know, because the 3D model of Helsinki, for example, it can be quite complex.
Yes.
It includes also trees.
Yes, exactly.
So how does the numerical grid look like for the simulation?
Yeah, so yeah, this problem is very, very complicated, but basically it has a mask. So the buildings, and I think also the trees are taking like a, so, no, okay. So for the buildings, of course, it's a mask. So it's like the flow cannot pass. But for the tree, it's a porous media approach.
Interesting. And you also said before that some models that were developed for certain cities, they can be ported to other cities.
Yes. So infuser.
But you would still need to calculate the flow field for the cities, right?
Sorry, wait. Yes. So this part you mean? Yeah. So of course it's doable, but one of the main. So the code infuser is open source, anyone can use. But the thing is, because still you have a lot of input data, you have to take into account if you go to the website, they provide a lot of. You cannot just directly use because you have to take into account whether some weather prediction, some prediction data from other outer sources. Yeah.
But also, if I can follow up on that, it's interesting because Helsinki is next to the sea.
Yeah, exactly. Coastal. Yeah.
It will have a large influence on the airflow.
Exactly. Yes. Yeah.
Thank you.
Yes, thank you for the talk. So for the respiratory airflows, this is a different code that you developed.
Yes. So here it was just OpenFOAM. Yeah, because yeah, so in OpenFOAM you can take realistic geometry, so there is almost no limitation on the geometry. So for this one, it's a basilisk. In most of these studies are either based on the basilisk or our own in-house Fortran front tracking code. Yeah, so it's either of them we use. Yeah, and we actually are also working now on OpenFOAM. So it's will be 3 codes. Yeah, Basilisk, OpenHouse, Fortran, and OpenFOAM. Yeah.
For example, like these kind of models are already implemented in OpenFOAM, or you have to implement yourself?
Yeah, so it's a bit. So if you speak about the OpenFOAM, so there is one kind of branch. It's called Rheology. So Rheology is so in Rheology community, it's very typical. If people use OpenFOAM, one of the most typical version of OpenFOAM, or like I don't know, it's called branch. Maybe branch OpenFOAM is called Rheology. So they develop a different viscoelastic, generalized non-Newtonian, elastoviscoplastic model, a lot of different models in that tool. And they also, in the one of the version, they also added the interface. So you can have interface. So in theory, you can also do some of the studies with the, and I started doing, and I did something. So some of the studies I could reproduce with the Rheology tool also. Yeah.
When you do the kind of atmospheric simulations that you have shown, for example, for the city, so okay, it's 2 questions.
This one.
Yeah, do you impose the flow
Pressure gradient.
or the pressure gradient?
Pressure.
And what do you have on top? Like, do you have a transpiration? Do you have like a free slate?
I think it's on the top. It's a free slip. Now I don't remember.
Can I ask you why you impose the pressure drop?
This is there are different ways to do, but usually in our group we do the pressure drop. But unfortunately, I cannot answer because I'm not doing myself urban flow simulations.
But you don't know if it's like a choice based on measurements or like.
So you mean okay? So are you saying like how to set specific case?
No, I'm saying what is more physical in terms of the boundary conditions that you apply.
On the top, you mean? Or on
the inlet outlet.
Okay. So for the inlet, so in our case, I think we can also do the inlet. So I don't know exactly like what would be there. Yeah.
It's not obvious. Okay.
Yeah.
Can you explain a bit more what is the role of the physical layer in the last part?
Yeah.
Okay, non-Newtonian.
Yeah. So mucus non-Newtonian, and actually the series there, it's very, very thin, so very difficult actually to resolve. And it is like Newtonian, but some studies show that making it slightly non-Newtonian make significant difference. That's one thing. So it means that mucus is not directly on the epithelial cells, but it's actually you have extra layer, and that even though very thin extra layer, it makes difference. It makes difference. So the rupture and the closure happening, dynamics actually affected by this extra layer. And of course, there's also the cilia motion. Black hair, so the mucus is moving by the cilia motion. And emission law is not here.
You need to impose a constant for it? Or it's
Yeah, so it depends. So it's not in this, but anyway. So if it's a airway closure, when it's closure, then you don't even need to impose anything, because what happens when the closure happening is that when there is no airflow. So you just destabilize, make a sine or cosine wave on the interface, and due to rail potential instability, it will just closure happen. So there's no need. But for the other one, when you want to rupture the plug, because then you have to apply the pressure gradient. So due to the pressure gradient, then the rupture is actually happening. So it depends on the case.
Also, I wanted to ask about the model for the dentist room, because you said your goal was in the end to have a 1D model.
Yes. Yes, for this one.
Yes.
Yes. So, so for the indoor flow studies, it's been there for a while, for a very long time, much, of course, before then the COVID happened. So people in HVAC, they have been studying for a lot, and they come up with some analytical solution. So it's basically a 1D solution, and you can see that it basically follows the same curve. It just go up, and after some time you reach some steady state. But what we saw when we perform our simulations and then we compare with this 1D simulation, then we saw that there is quite discrepancy. So the one of the main differences is that when they do 1D simulation, it's assumed that the flow is highly homogeneous in the flow. So all the concentration is homogenized through the room, but in reality, it's not homogenized. It will not never homogenize. So, and because of that, there is a huge discrepancy between the analytical solution and the other. So there are so many studies which try to improve, but then I guess with the more detailed LES studies, this 1D model can be improved even more. But the idea is that you come up with the 1D model, which can, depending on what are different conditions, so that you have this 1D model, which can predict the slope up and down, it's up and down model.
Another question? Yeah.
Yeah.